Ever wondered if the cloaking devices from science fiction could ever become reality? Prepare to have your perceptions challenged. What was once confined to the realms of fantasy is now a tangible frontier in scientific research, with real-world progress being made in the development of invisible cloaking technology. This isn't just about optical illusions. It's a deep dive into the cutting-edge physics and engineering that are redefining what it means to be unseen. For decades, invisibility has been a staple of speculative fiction, sparking imaginations worldwide. Yet, the journey from theoretical concept to practical application is a testament to human ingenuity. We're witnessing a remarkable evolution, moving beyond basic optical tricks and camouflage to groundbreaking research in advanced materials and sophisticated cloaking systems. This explainer video will demystify the science, showcasing how engineers and physicists are bending light, sound, and even time to make objects disappear. The core challenge of invisibility is simple yet profound. How do you make something undetectable? The answer lies in manipulating the waves that interact with an object, whether they are light waves, sound waves, or electromagnetic waves. By guiding these waves around an object, or by making the object indistinguishable from its background, scientists are progressively turning the impossible into the plausible. This field is a vibrant intersection of optics, materials, science, nanotechnology, and computational physics, pushing the boundaries of what we thought was achievable. At the forefront of this revolution are metamaterials, engineered substances designed with properties not found in nature. Unlike conventional materials that interact with light based on their atomic composition, metamaterials derive their unique abilities from their meticulously designed sub-wavelength structures. These structures, often smaller than the wavelength of light itself, allow metamaterials to bend light in extraordinary ways, making them the cornerstone of many cloaking technologies. The key property of metamaterials is their ability to exhibit a negative refractive index. In normal materials, light bends in one direction when it passes from one medium to another. With a negative refractive index, light bends in the opposite direction. Imagine light waves flowing around an object as if it weren't there, converging on the other side as if they had traveled through empty space. This optical sleight of hand is what allows metamaterials to render objects invisible under specific conditions, effectively guiding light waves around an object and making it appear as if the light travels uninterrupted. The rise of nanotechnology has been absolutely critical to the advancement of cloaking. It's one thing to theorize about metamaterials. It's another to fabricate them with the precision required to manipulate light at its fundamental level. Nanotechnology enables scientists to engineer and fabricate materials with precise structures at the molecular and atomic scale. This unprecedented control allows for the creation of intricate patterns and arrangements that dictate how light interacts with the material. By working at the nanoscale, researchers can design and build ultra-thin cloaking layers, often just a few nanometers thick. These layers can be tuned to specific wavelengths, offering unprecedented control over light's behavior. This level of precision is essential for creating the complex geometries needed for negative refractive index effects and for developing materials that can effectively hide an object from detection. Without the advancements in nanofabrication, many of the theoretical concepts of cloaking would remain just that, concepts. Beyond passive material manipulation, the integration of optics with computational power has given rise to digital and active cloaking systems. These systems represent a dynamic approach to invisibility, moving beyond static materials to real-time environmental adaptation. Instead of simply bending light, these technologies actively capture and project the surrounding environment onto an object, making it blend seamlessly into its surroundings. Imagine an object covered in high-resolution cameras and flexible displays. The cameras capture the background scenery from various angles, and sophisticated algorithms process this data in real time. This processed background image is then projected onto the object's surface using the integrated displays. The result is a dynamic camouflage that adapts instantly to changes in the environment, effectively making the object disappear to the naked eye. This approach leverages advancements in high-speed computing, advanced display technologies, and sophisticated image processing, offering a versatile solution for visual concealment in complex and changing environments. Invisibility isn't just about light. It extends to other forms of wave energy, including sound. Acoustic cloaking aims to make objects invisible to sound waves, creating silent zones around them. Just as optical cloaks guide light, acoustic cloaks are designed with structures that can manipulate sound waves, bending them around an object rather than allowing them to reflect or scatter. This prevents the object from casting an acoustic shadow or producing echoes, effectively rendering it acoustically undetectable. The principles are analogous to optical cloaking, but applied to sound waves. Researchers are developing acoustic metamaterials that can redirect sound waves, creating a path of least resistance around an object. This technology has profound implications beyond military stealth, including applications in noise cancellation, making submarines truly silent for underwater exploration, or even improving medical imaging by creating zones free from acoustic interference. Imagine a concert hall where sound is perfectly directed, or a quiet zone in a bustling city. Acoustic cloaking could make it possible. For decades, radar cloaking has been a cornerstone of military stealth technology, making aircraft and ships virtually invisible to radar systems. Radar works by emitting radio waves and detecting the reflections that bounce back from objects. Radar cloaking, therefore, focuses on minimizing or eliminating these reflections. This is achieved through a combination of specialized materials and aerodynamic designs that redirect or absorb radar waves. Stealth aircraft, for instance, are designed with angular surfaces that scatter radar waves in directions away from the radar receiver rather than reflecting them directly back. Additionally, they incorporate radar-absorbent materials, RAM, that convert radar energy into heat, effectively absorbing the waves instead of reflecting them. By redirecting radio waves around an object or absorbing them, stealth technology significantly reduces an object's radar cross-section, making it appear as small as a bird or even completely disappear from radar screens. This continuous arms race between radar detection and cloaking drives innovation in both fields. In a world increasingly reliant on infrared cameras for surveillance, security, and even search and rescue, thermal cloaking offers a crucial layer of invisibility. This technique hides objects from infrared detection by controlling how heat is emitted or absorbed, making them blend seamlessly into their surroundings. Every object with a temperature above absolute zero emits infrared radiation, creating a unique thermal signature. Thermal cloaking aims to mask or mimic this signature. This can be achieved through various methods, including active cooling or heating elements that match the ambient temperature, or by using specialized materials that can dynamically adjust their emissivity. For example, a thermal cloak might absorb heat from one side of an object and re-emit it on the other, creating a uniform thermal profile that matches the background. This technology has significant applications in military operations, preventing detection by thermal imaging systems, but also in civilian uses like improving energy efficiency in buildings by controlling heat loss or gain, or even in personal protective equipment. Pushing the boundaries of cloaking technology even further, a novel concept involves invisibility drones. This isn't just about making a drone disappear, it's about creating an autonomous platform that can dynamically adapt its cloaking capabilities. This cutting-edge concept utilizes an autonomous drone platform equipped with microwave-thin, customizable metasurfaces. These metasurfaces can be reconfigured in real time to manipulate electromagnetic waves, offering a level of adaptability far beyond static cloaks. What makes this truly revolutionary is its aeroamphibious nature. Such a cloak could potentially operate in air, water, or even across different electromagnetic spectra. The drone's onboard intelligence, powered by probabilistic reasoning, would allow it to analyze its environment and adapt its metasurface configuration to neutralize external inputs and maintain its invisibility across various situations. This multidimensional, adaptive cloaking system represents a significant leap, overcoming current one-dimensional limitations and hinting at a future where cloaking is not just passive, but intelligently responsive. Perhaps the most mind-bending concept in cloaking research is the time cloak. Unlike spatial cloaking, which hides objects in space, a time cloak aims to mask events in time, making them undetectable. Imagine a brief event occurring, but for a fleeting moment, it's as if that event never happened. Researchers at Cornell University demonstrated a rudimentary form of this by manipulating light pulses in fiber optics. They used fiber optics to split a beam of light in two, accelerating one part and decelerating the other. This created a temporary gap, or hole, in the light stream. If an event occurred within this gap, it would be completely masked, as the light waves would reform on the other side as if nothing had interrupted them. Neither the faster nor the slower part of the beam is visible in the time lens created by other beams traveling through the cable. This masks an event in time, effectively creating a temporal blind spot. While still in its nascent stages, time cloaking has profound theoretical implications for secure communication, data transmission, and even the fundamental understanding of space-time. Despite the breathtaking progress, the journey toward ubiquitous, broadband, and practical cloaking technology is far from over. Significant challenges remain, and much of the ongoing work concerns finding solutions to the technology's current limitations. One major hurdle is achieving broadband cloaking, making an object invisible across the entire visible light spectrum or a wide range of electromagnetic frequencies, rather than just a single wavelength. Current metamaterials often work effectively only for narrow frequency bands. Another challenge is scalability and manufacturing. Fabricating metamaterials with the required precision over large areas remains complex and expensive. Furthermore, many cloaking designs are directional, meaning they only work from specific viewing angles. Achieving omnidirectional invisibility is a much more complex problem. For active systems, power requirements and the need for real-time, high-speed processing are significant engineering hurdles. The future of cloaking lies in overcoming these limitations, developing new materials, refining fabrication techniques, and integrating artificial intelligence for adaptive, intelligent cloaking systems. The world of invisibility is rapidly transitioning from science fiction to scientific fact, driven by relentless innovation and groundbreaking research. From the intricate designs of metamaterials to the dynamic capabilities of digital cloaking and the mind-bending concept of time cloaks, we are witnessing a revolution in how we perceive and interact with our physical world. The implications for defense, communication, energy, and even everyday life are immense and still largely unexplored. Are you ready to delve deeper into the future of unseen technology? Subscribe to our channel for more in-depth explainers on cutting-edge tech. Hit the notification bell so you don't miss our next video exploring the frontiers of science. Share your thoughts in the comments below. What application of cloaking technology excites you the most? Let's continue this conversation about the unseen revolution.